Sure.
Yeah, sure. Okay.
It's a great pleasure to welcome the University, where he's the Jokel Chair Professor in Electrical Engineering, and he also heads the Center for Artificial Intelligence and the Data Science Center, jointly with Google.
Google put some donation.
Put some donation. Yeah. So Meir's teaching and research interests are in statistical signal processing, network information theory, especially universal processing aspects, which he has been working on for a long time. Universal coding, data compression, and all affiliated fields. Now, one of the first papers of yours that I read was this paper with Meir, Michael Gutman on universal prediction of individual sequences, which in fact won the information theory best paper award in 1993. I think the paper had appeared a year earlier, and in fact, there has maintained an abiding interest in universal processing for a long time now, and different aspects of this work even now touch upon universal processing in one way or the other. Now, in addition to his academic career, which is extremely rich, he has two successful parallel careers. One is as an entrepreneur in high-tech industry, and the other one is in the movie industry. In fact, he's the only information theorist I know of, and probably will ever know, who has won an Oscar. And he's probably the only information theorist in the world today who ever received an Oscar. He comes in 2020 for the scientific and engineering category, right? And in fact, I think the only Oscar winner worldwide with whom I've had the pleasure of shaking hands. So I'll welcome, and we look forward to your talk here.
Okay. Thank you very much, Prakash. It's the Scientific and Engineering Award of the Academy of Motion Pictures, Arts and Science. That's the official name.
Yeah.
It's a big name. And I also didn't know about that until we got it. It turned out that award is given, it started the year after they started with the Oscar in 1930. The Oscar started in 1929. And it is in the movie industry during the years and many engineering, breakthroughs, so they used all the available technologies that exist. And, people that got that award were very famous, changed the world, like Dolby kind of things, Adobe in some certain ways, and other. So it's a respectable list of people, and I was glad to get it for the technology we developed in a startup called Amin. But let's go to the thing that I'm going to talk today. Prakash correctly said, I'm working on what's called universal coding or universal approach in information theory for many years. And I did it a lot in the 90s, mostly with Neri Merchav, also with others. Then I continued on some different tracks later on. Then I also did other things. When the AI started, when the modern AI, neural networks, which was, people say it's 2012, this was like the breakthrough paper on deep neural networks. A couple of years later, I thought that the universal coding, universal prediction must be related to what's going on in this modern AI. I must confess that I still don't understand exactly everything there, and the talk today I will discuss that. But I was naive. So I told my student, look, here is this, what's happening, and here we have this theory on universal prediction. I suspect there is some kind of a copy and paste that we have to do. Take the results there, modify them a little bit, add the issue of side information, add the issue of training and tests, and we will explain what's going on. Luckily, this is not the case. Luckily, what happened in those large models, and those models are becoming larger and larger, is much more interesting, and I will try to touch it a little bit in my talk, and there are some results, but also many open questions. Okay, so let's go to the talk, but I hope you will forgive me for mentioning that next week is a year for what happened in Israel on October 7th, a brutal attack of the Hamas on peaceful places. One of the places is Be'eri, which is right here. This is one of my favorite locations in Israel. I know many people there. I'm visiting there often, riding bikes. This is the bike shop that we used to have there. This is the party that many people were killed, but not only that, a special woman lived in Be'eri, Vivian Silver. She dedicated all her life to peace. She was working day and night to take children from Gaza and other people in Gaza that were sick to be treated in Israeli hospitals. She was getting back and forth. And she was brutally murdered by the Hamas on October 7th, a 70 years old woman. So I dedicate this talk. This is a friend of her, an Arab friend of her. This is Vivian Silver. This is one of the pictures came out. This is Vivian. This is a friend of her who she took care of.
I read about that. Her husband also.
No, this is another couple. It turns out that area around Gaza, I mean, in Israel, we have many political disagreements, like in any country. But the people that live around Gaza, in the villages there, most of them were working for peace. And they were the ones that were killed, on this terrible day. Vivian Silver was one of the famous of them. I knew her personally. I dedicate this talk. Okay, now let's go to non-political things. In the talk, as I said, I have actually two messages. The first message is what I thought to begin with, how to bring all learning theory, especially statistical learning theory, in information theoretic terminology. I must say that when I heard about, or when I read papers on learning theory, on what's called pack learning, I didn't like it. I thought it's too cumbersome, too combinatorial in a way. And I always believe that information theory is the right way to approach statistical learning, and I will try to convince you. That's the first message. But as I said, this was not enough. That may explain the classical situation, the situation where we have a small, limited hypothesis class. In the modern AI, we have big models, huge models. The number of parameters is much, much larger than the available data, and it keeps growing. And the mystery is that although it keeps growing, it performs better. So we don't have this phenomena of overfitting, or we do have it, but not always. For practical reasons, it works. It gives, all of you have tried the GPT and other things. How come? I'll try to touch that in the second part of the talk. Okay, universality. Rakesh was right. I'm working on this problem for quite a few years. And in a way, you can say that what is universality, why we call it universality. In many problems, especially information theory, the solution and the performance depend on the model. We have to assume some statistical probabilistic model to the data, to the channels, whatever, and we can get the optimal performance if you know the model. What universal scheme are doing? They are model independent. That's why they're called universal. They don't depend on the model, but they strive to attain the performance as if you know the model. That's essentially the concept. Sometimes you can do it, sometimes you can not doing that, but that's the idea of universality. And as I said, I'm working on that over 30 years with Neri and others. And I got inspired by those three great people. Actually, I got to this subject by meeting Yoram Arissanen when I was a PhD student, and he sort of brought me to then. Then I had some contact with Tom Cover. Actually, the last one that I met was, although he's an Israeli, was Jacob Ziv. I met him only when I went back to Israel later in the 90s. And again, he was another source of inspiration. Unfortunately, all the three of them are not with us anymore. Okay, universality started, or the the place where it shines is the problem of lossless source coding, which, as you know, and as I will emphasize, is completely related to the problem of optimal online prediction with log loss. Okay, so I'll start with that simple problem, and from there we will go on. So what is the source coding problem? Very simple. It's always nice to start with things that everybody knows. So we have a sequence, x1 to xn, and there is some probability law for that sequence, and we know that probability. And indeed, in that case, we can get the optimal performance, which is the entropy, and we know how to do it. We can use this known probability distribution to design Huffman code, arithmetic code, whatever, and we can achieve the entropy within, let's say, O of 1 over n bits, where n is the sequence length. What do we do when we don't know p, or even when it doesn't exist? Again, as you probably know, each coder that we come up with is essentially assigning a probability distribution to the data. You can think of why is it because of Kraft's inequality. So coding or assigning probability to the data are the same things. Q of x is 2 to the minus lx, where L is the length of the code word that you associate to x. And if you use any Q instead of P, you pay. And the amount you pay is the divergence between P and Q, which actually tells you that the best thing to do is to take Q equal P. Then it will make the overhead 0. But you don't know P, so how to choose Q optimally? And here is the concept of universal probability. What we are looking for is a single probability, universal, Q, which can work no matter what P is, and even if it is not existent. Simple. I'll try to build that Q. I mean, how you find that Q? I'll try to build that Q in stages. The simplest way to find a Q, a good Q, a universal Q, is under the assumption that there is some model class, which actually what we are saying, we don't know the probability distribution of the data, but we know that it belongs to some class of probability distributions. Okay, and we will see how good we can do a universal coder in that situation. But that's not enough, as we said. Modern AI are using large classes. So I'll discuss a little bit the way it was considered previously in the classical work, let's say the work especially of Ziv, where you try to do universal with respect to a large class of model, even all ergodic sources, but you do it in a way which, as I will discuss, is just extending the model complexity as you have more data, which is probably not the right way to look at that problem. And then I will get to the main message of the talk, which I call twice multiple or hierarchical universality. Okay, so that's how we will go from the assumption that we have a class, that now we have a big class, but we consider that in a very, I would say, straightforward way, and then we will get to the essence of what I like to talk about. I have two slides that I will just skip over them, which just tell you that lossless source coding and prediction with log loss are the same problem. And the reason I'm skipping it is because of time, but you mentioned the work that I did with Neri Merchav. We wrote a survey paper when it was 50 years to information theory, Neri and I. Yeah. And at that time, we sort of apologized why we are using prediction with log loss. We call it information loss. We try to justify it by all different things because people were using other losses, like, Hamming loss, square error loss, other losses. And we had to prove that by using the log loss, you can actually get results on other losses function, all those excuses. Now we don't have to make any excuse. All the models that people are now training are using log loss. GPT, prediction, the criterion is, they call it cross entropy, but it's essentially log loss. Log loss is now universally, right, accepted as the right loss function. Again, there are some justification for that, but that's what people are using in practice. If you use GPT, that's what they're doing. And actually, a training GPT is nothing than universal prediction with log loss, but with large alphabet. And I said we have to apologize. Indeed, if you use log loss, the claim is that the log loss give you as prediction, not a value, it gives you a probability distribution. Take this probability distribution and use it for a base decision problem on the loss that you like. And the claim is that this is the optimal solution for general loss. Well, almost. It doesn't work all the time. It doesn't work when the loss is discontinuous. It doesn't work all the time. When the loss is discontinuous, you have to randomize it a little bit. And that's how you translate log loss to other loss functions. And we can continue with log loss and feel happy about. Okay, so let's start with, as I said, the simplest problem. We are having a class of models, and we want to be universal with respect to a given model class. Okay, here it is. Set of models, probability distribution of the data, defined by some set of parameters. Theta is just the index of the model class. Now, the fact that we have hypothesis class, which are probability distribution, doesn't necessarily mean that the data comes from those models in the class. And you can actually go again at 3 levels. What we call the stochastic setting is indeed when the data is coming from one of the models of the class, but we don't know which model. But then we can say, oh, why is that? The data can come from probability distribution outside the class, but we still have this class to explain the data, which comes as a set from probability distribution outside the class. This is was called misspecified setting. This is actually what computer scientists like. They have a hypothesis class, and then they said data is coming from some IID distribution, which may not be in the class. But then there is even an extreme case of individual setting, where you don't assume anything. The data is what is the data. Yeah, and you can think that the individual setting is like assuming that the data is coming from any joint probability, which can also be deterministic, and put everything on that particular sequence that you have. But the notion of individual sequence is also very strong, and actually it was very surprising to me when I first saw result on that. I considered that. So we have a class, and we have 3 layers of assumption how the data is generated. In information theory, we are not just saying, let's try some predictor and that prove how it performs. We are looking for the optimal solution. By the way, I did mention that, of course, the elephant in the room is how you choose the model class. And that's what I will talk about it later on. That's the most important issue. But now we have a model class. And we have 3 assumptions on how the data is generated. Forgive me for being so small. But in the stochastic setting, the solution is always min-max. We want to use, we are looking for the universal probability Q, which can work no matter what the truth is, right? So the first criterion is you min over Q, max over theta. This is the index of the class, of the regret. What is the regret? The log loss that you get, minus log Q, minus the regret that the person that knows theta gets. So you get log of p theta over Q, it's minus log Q, minus log p theta. So that's the divergence, you min-max it. That's in the stochastic setting, very simple. In the mismatch setting, you get a slightly different criterion, where you compare yourself not to the true theta, because the true theta is outside the hypothesis class, you compare yourself to the projection of the true distribution over your class. And then you do again min-max. And what do you do in the individual setting? The same thing. You compare yourself to the projection of the individual sequence over the class. What it is, it's the maximum likelihood for that sequence of models in the class. So the difference between those 3 settings is what you compare yourself to. You are looking for a Q, in the worst case, that can compete with the best thing somebody can do if you know the right model. Again, either it's the true model or the best approximation of the true model. Okay?
So the second one, you start with P, which is like somewhere outside.
Yeah, and you project it like this.
Then you project it, and then you get the theta of P. That's the projection. right?
Yeah, theta of P is the projection of P over the class theta.
And that is done separately using that.
There is some projection. I don't know P. Remember, I don't know P. But I don't care about that. What I care about is projection over theta. Because that's my constraint. I have an hypothesis class. I want to explain some probability distribution outside the class using my class. So I compare my Q to the projection, which is the best I could have done if I knew P. If I knew P and I'm constrained to find explanation in the class, that's the best I can do. Similarly here.
So you take the maximum with respect to P, so that
Exactly. The maximum over any P. Okay. P also have some assumption. Computer scientists usually say some IID distribution. P also must have some assumption, or if it doesn't have any assumption, you got to the individual case. The individual case says, now I have the sequence, and the projection of the individual sequence over the class is just the maximum likelihood. You see, just here, it's the maximum likelihood fit of a parameter to that particular sequence. Okay, so all those three criterion are similar. And what's nice in the information theoretic approach, yeah, go ahead and ask.
But if I may, our goal is to construct Q, right?
Q, exactly. Q is the universal probability. Okay, let's speak about it for a second philosophically. As I said, we have a class, many probability distributions there. I want to replace them by a single probability distribution, which I can use no matter what other theta I should have chosen depending on my assumption. But it's universal, a single one. In a way, it represents all the models in the class. Okay, and when you see the solution, you will understand. All those three problems have been solved explicitly. Again, that's one of the good things in the approach, the information theoretic approach compared to the learning theory approach. We try to find the criterion, to find what achieve the criterion, or at least upper bound it. In this case, we can indeed define the criterion, and we were able to solve. In the stochastic case, the solution turned out to be, actually was suggested by Gallagher, who is a student. I learned about this solution when I took the information theory class with Gallagher back in '85. And later on, when I worked on that, he told me that the paper that he wrote on that was rejected. But he was, he didn't have I don't know, the energy to correct it and resubmit it. So what he did, he just distributed as class note to the student in the class. And that's how I learned about that result. I didn't appreciate it then, but indeed Gallagher's result, later on it was rewritten by Davison and others, but he was the original one. It was published only as class notes in MIT information theory classes. By the way, it doesn't mean that any paper that got rejected is a good paper. Some good papers are getting rejected. Anyway, so the solution is very intuitive. The solution, this Q that we are looking, is just some kind of a Bayesian mixtures over all the models in the class. And the Bayesian measure is the one that sort of maximizes the mutual information between theta and x. That's why this theorem is called the redundancy capacity theorem. The redundancy that you get is the capacity of this class of channels. And W is the one that is the capacity achieving prior. And the redundancy that you pay is indeed this capacity. Now you can say, why min-max? In log loss, we have another great thing, is that min-max, although it's worst case, it's not really a worst case. It's a typical case. And this is why we have, Rissanen started that, and then Meir and myself proved what's called the strong capacity redundancy theorem. And that's simple. In the misspecified setting, I must confess, we in information theory didn't look at it. The computer sciences learning theory did look at it. Baron mentioned it by some paper in '98, but really didn't analyze it. So as part of my trial to do cut and paste, I had to sort of clean up a few things. So one of the things to clean up was this. And with Yuri Polyansky and then Amichai Pensky, we solved that problem and also find algorithm for that. And again, we have an explicit solution. The solution is sort of a Bayesian distribution, but not over theta, but over the B class of all the models that can be outside. But that distribution maximizes not the mutual information, but mutual information with penalty. And the penalty tells you if you are far away from the class, you pay a lot. You pay with a minus. So the result is a mixture that concentrates around the hypothesis class. And a result that I proved with, it's not here, the result I proved with Yuri is that essentially the capacity, the hypothesis class represent also the performance in this case. So
that difference is always non-negative, or it can.
Of course, because it's divergency, right? We have divergence.
Different.
You want that to be, since you want to maximize,
yeah.
You cannot allow yourself this to be big, right? And how you make it not to be big? By concentrating your prior essentially on the smallest, so that the divergence will be close to zero. So the solution is not really there. Actually, I did it with Yuri, and then with Amichai, we developed a variation of Harimoto Blaut to calculate that tilted capacity or penalized capacity. And the results turn out to be, as I said, concentrating around the hypothesis class with a little bit outside. So that's the misspecified. And again, there is some kind of strong result on that. And the individual setting was actually proven by Starkov in '87. And it's what known the normalized maximum likelihood. And again, it has some redundancy gamma, which is a little bit greater than the capacity. And again, there is some strong version of that that actually proved with Marcelo Weinberger a while ago. What you want to remember, oh, time is sort of 61. I can go after the time. Oh, okay, great. So I like that because then I can explain everything that you will fully understand. So we have three terms, right? C, the capacity of the hypothesis class. We have F, the mismatch capacity, and we have gamma, the individual's penalty, the individual redundancy. If the class is defined by smooth parametric models, so we have parameters that define how the probabilities in the class behave, exponential families or whatever. Actually, this was already shown by Rissanen. Both C and gamma behave as k/2 log n. So if you have a data of size n and you have the number of parameters is k, that's the penalty that you pay. And even gamma looks like that. It's a little bit bigger. And the reason it's bigger is because the reference is smaller, right? You compare yourself to the maximum likelihood, not to the true probability, but it essentially behave similarly. F is in those cases like C. And the point is that, I mean, if you intuitively want to understand why the penalty with smooth parametric models behave like k/2 log n, you can say the following. What is the meaning of capacity? The meaning of capacity is the maximal number of points that you can transmit and can distinguish between them, right? Now, if you have a set of parametric models, how close can the parameters be and still be distinguishable? If you want to do, estimation of those parameters, we know that in many cases, the estimation error behave like 1/√n, where n is data size. This is the some variation of it. So you can sample each parameter at the distance of 1/√n between the parameter points. And if the range of that parameter is finite, you have about √n values for each parameters. You have k parameters, you have √n to the power of k. Take the log of it, you get k/2 log n. So that's another intuitive thing. One important thing to say is that if you don't use the optimal solution for the stochastic case is the Bayesian mixture. But you use this Bayesian mixture even for the other cases, you get pretty good results.
So in some cases,
Yeah.
turns out to be the conjugate price.
Yeah.
Is it true for this new class of function that you had?
For the F,
Uh-huh.
no, there it looks much different. The reason you get the conjugate prior is because this term, you see, this term is sort of doesn't depend on theta. And so the prior that you have to choose it must be proportional to one of the square root of the Fisher information. The Fisher information in multinomial distributions or in Gaussian distribution generates some kind of a conjugate prior. Okay, but you had a good point. My claim would be that in many cases, not in all of the cases, maybe I'll go here, you can ask how come a Bayesian mixture over the probability distributions work for prediction. Well, okay, computer scientists will say, we are using what's called the ERM. We just have data, we fit the best model for it over the training and then use it. Continue doing that. What the Bayesian mixture tell you to do is the following, not to pick a single theta. So here we try to predict, to assign a probability to xt given the past. When we work the machinery of probability theory, we actually have to weight all the models that you want to predict with according to a weight that is proportional on one hand to the prior, but that's not so strong, and on the way that that model fitted the training. So if the fit to the training is such that the ERM, the maximum likelihood, is very strong compared to all other models, you can replace this mixture by a delta function over that maximum, because this thing go exponentially with respect to the maximum, right? That's the issue how you do a Laplace approximation and all those things, but not always. That may explain why sometimes ERM works. What all learning people do, they're doing ERM. They're running all this, trying to estimate that ERM. So you see this one interpretation why doing Bayesian and doing prediction with that is actually a little better, because we don't pick a single value for the parameter, we also weight the others. We weight them according to how well they fitted the data that we already have. And we also have a prior, but you can see that in many cases the prior, I mean, it's not so crucial. I mean, the sensitivity to the prior is not so strong. It's nice to choose the prior. Sometimes it gives you an analytical solution for the predictor. As you mentioned, it's conjugate prior, but it's not really crucial. And here is a slide I like when I try to explain my student, again, why Bayesian work. Another explanation why Bayesian work. To represent, or why universal probability is a good idea. Suppose my class is very degenerate. I only need two models in the class, P1 and P2. But those models are really different. They're far away from each other. The divergence between P1 and P2 is very large. Away. They don't resemble each other. Nevertheless, I can represent both of them by this Q, which is half P1 plus half P2. And if I do that, what happens is the divergence between Q and P1 and the divergence between Q and P2 is less than 1. That's simple calculation. If you want to, now let's go to information theory and the intuition from coding. Of course, you can build a coder that the first bit tell you should I choose P1 or P2, and then I choose either P1 or P2 depending on the data. If P1 on that specific X is larger than P2, I tell you by one bit do P1, and then encode the data with P1. And in this case, I paid only one bit on top of somebody that knew to choose P1 upfront. So I pay only one bit, and I can do it no matter what P1 and P2 were. And again, it tells you that sometimes it's nice to think on the divergence as a term for metric, but it's not really a metric. And sometimes it sort of surprises us. That intuition I like, and in a way, it explains the possibility to come up with a universal probability. We have a single probability Q that can represent many, many probability distributions up to some distance. And that distance is this capacity that we have shown. And the example is, you mentioned conjugate prior. If you take the Bernoulli case, of course, the prior is the Jeffreys prior. It's a Dirichlet prior. It's a Dirichlet 1/2. And the predictor is very intuitive, the Krzyzewski-Trofimov, count how many zeros and one you head up to the counts and normalize, and we will get back to that later, very simple. And again, the intuitive that I said before. Okay.
But this thing also has the benefit that if you have the Q probability of a sequence of length n,
Yeah,
then when you get additional data, you don't have to redo the calculation.
yeah, you can do it sequentially, yeah, exactly. Okay. But that's, by the way, it's asymptotic, and okay, now, there are many interesting details that, okay, you sure I have more time because I want to get to the interesting stuff. Okay, give me 15 more minutes and then we'll be okay. Good. So as I said, when in this task of cleaning up things, I said, okay, that's fine. What I just described is like assigning probability to the entire sequence, like that Q. But in learning, you usually have training and test. Okay, you could say that, oh, the way we assign probability to the entire sequence, you can consider on that as online learning. Like I predict the first symbol, then the second given the first, and so on. Fine, online learning is very interesting. Again, the common situation in learning is training and test. Can we, as in the cleaning up, can we extend the theory that we had in the 90s or whatever to that situation? And why not? We have training, xn, yn. The predictor is a probability for the next label given the new feature plus the training. Again, we use the log loss and we consider what's called the test error. And here is a criterion for the stochastic setting. We want to minimize over Q, the conditional probability, maximize over theta of the expected value, and that's important, of the regret minus log of Q minus log of P theta for the test symbol. So you can say where the training enters. The comparison here was only on the test, right, on yn. The training enters with this expectation. The expectation here is on both the training and the test. And now, when we compare the information theoretic approach to the learning theory approach, the learning theory PAC, what they call PAC, is they want to have with high probability over the training to get a small error on the test. So the wish to get a small error on the test is from here, right? This is the error on the test. And instead of high probability on the training, we do expectation on the training, which give us explicit results. And moving from expectation to high probability is not so difficult. Just use some concentration theorem and you are done. Okay, good. Yeah, a question.
So in all of this, you have the data, and the data already contains some information.
Yeah. Yeah.
You don't bring them as constraints in the training.
No, it comes essentially through this expectation here. The old data comes as expectation because, yeah, but the expectation is with P theta that you don't know. Look, I'm asking, you see, here is min max. I want to minimize over Q, max over theta,
yeah,
which is the explanation for both training and the test. But the error is measured only on the test.
No, I understand. I'm saying, but the data itself has some empirical moment.
Of course. It enters in the solution. But this is the criteria.
Okay.
And then when we look at the solution, we see that all this intuition that you had, catching the moment, getting the estimation, happened. But the solution for this, but when you put this criterion, it makes sense, right? I'm interested in the error on the test, but I want that it will be since I come up with a single procedure, Q, I wanted that it work no matter what the training is. You depend on the training, but I want to take it into consideration. So I put this criterion, and I can put a similar criterion for the mismatch, right, on the projection. We can put some criterion over the individual setting, but this is a little bit questionable, and I don't want to get into that because here we have a set of papers that deal with a prediction of a single test with individual sequence, so I'll skip it. But let me tell you the solution. The solution, at least in the stochastic setting, also on the misspecified stochastic setting, is again a Bayesian mixture, but now the weight, this W, does not maximize the mutual information between theta and the entire observation. It maximizes the mutual information between theta and the test, given the training and the available feature sequence. And of course, the mutual information, everything is with expectation here, and I call it predictive capacity. A similar thing is with the mismatch case. In the individual setting, I'll skip because I can talk 2 lectures on the individual setting. We'll skip it later for interesting. So again, we have those results. And intuitively, as you said, the role of training. You can say that the role of training, when you think in this learning situation, is to, in a way, focus you into a smaller subset of the hypothesis class. That's what essentially the training is doing to you. Concentrating on some portion of the training of the hypothesis class, and then for the test, you do some, in a way, min-max on that. And another interesting result, which I will use later on, we have this result that if you are able to, in a way, universally compress the training, as we show with universal source coding, and the overhead sort of does not change much as you increase the data. The derivative with respect to the data size goes to 0, then you can prove that you have good predictor. So remember that, because I'll give example. For us information theorists, sometimes it's nice to think on the problem on the learning problem, on how universally we can compress the training. We have data. If we know how to universally compress it, it implies the ability to learn it, even in complicated situations, which I'll explain, which I'll describe later on.
Just to understand what you just said. So in effect, first, when you reduce the size of the hypothesis class, then the family of distributions over which we have to place shrinks, and
Which is good, because you have data.
The estimation then is in the class that we are interested in, the number of elements in the family shrinks.
Yeah.
And then you get consistency because of the second.
Exactly.
That's the idea.
Yeah, exactly. And there is some relation to VC dimension, again, I'll skip, which tells you that the information theoretic approach is stronger than the learning theory approach.
I don't know, venture capitalists came into play here.
VC, people don't know. Okay. The other, I'll finish then and I'll switch gear. The other interesting thing is that there are some, as I said, when I was cleaning up things, there are differences between the situation of assigning probability to the class and doing online learning and doing training and test. Even in that Bernoulli example, we got that Krzyzewski-Trofimov thing, or Jeffreys prior, or conjugate prior, whatever. When we look at the criterion that I presented, that now the weight maximizes the conditional mutual information, the resulting weight turned out to be not conjugate prior. Actually, I cannot evaluate it explicitly, even asymptotically, that conditional mutual information to maximize it. Maybe somebody else can evaluate that. So what we did, we said, let's calculate it. So we come up with, again, a variation of a remote Blaut algorithm. We calculate the prior that maximizes the conditional capacity. And surprisingly, the prior that we got looks like this. This is theta between 0 and 1. For that example of Bernoulli, this theta between 0 and 1. Jeffreys prior, which is solution in the online prediction, behave like this, something like proportional to 1 over square root of theta 1 minus theta. Smoother. I mean, it's also high at the edges, goes to infinity at the edges, but sort of smooth in the middle. Here, it gets infinity, probably very high delta function at the edges, but in between, it's almost constant. And there is some Gibbs kind phenomena here. And the other interesting thing is when you do conjugate prior, the predictor comes up to be what's called add beta. Count the number of zeros and one and add some constant. And the constant depends on the parameter of the prior, Hierarchical, whatever. Here, you don't get add beta. Actually, there is a proof that the best add beta doesn't attain the optimal performance. This was done actually by Krzyzewski back in the 90s when he visited me after the I don't know, so the Soviet Union collapsed. And he showed that the best beta for that problem it doesn't achieve the optimal performance. And indeed, when you use this prior, this slide show you the effective beta. Sort of the beta depend on the empirical probability. So it's not add beta. So for different empirical probability, you have to change the number, the count of zeros and one by a different number and then normalize. So it's not an add beta, and but nevertheless, that by the way solved or improved the best known solution until our work, the experimental work, was by Brass and Sauer, two people, mathematicians that did it in a very terrible way of Bernstein polynomials or whatever, which I never understood, and they got sort of the optimal performance, which is 1 over 2n, but we got it with our thing easily. Okay. Good. So now let's go to the real thing, and I have only half an hour. Okay, a little less, 25 minutes, fine. Large class of models.
Oh, I'm sorry, one more question. One of the things, the estimator that you mentioned is the feature.
This is for the online.
Yeah. Now, there's also, when you have this large class of models,
Yes.
if you don't observe some data, there are some zeros, how do you get rid of those? So then they used to be these Turing good.
Yeah. I'll get to that for large. Okay. The example that you now mentioned, if the alphabet is very large,
Yes.
for me, it's a large class of models. The capacity goes to infinity or proportional to the number of unknowns of the alphabet, which will be larger than your data size. That's again the mastery. And that's exactly I'm going to tackle. I'll go to this example. Exact example. Okay, so again, Prakash asked the right question. So far, we had a given class of models, which is not too large. It is we measure the richness of that class of model by, let's say, the capacity, by gamma, by F. And that capacity F or gamma were negligible with respect to N. N is the data size in order that we can declare learnability. If we say that's negligible compared to the data size, we say we are okay. We don't pay much. But now we have very large class of models. The number of parameters is said trillion. One way to think about the large class model, which I keep repeating, is that it's essentially composed over subclasses that are smaller. Why not? Sort of divide it into subclasses. And now we have many subclasses. Each of them has some capacity or F or gamma or whatever. Sometimes those subclasses are nested. That's the example, let's say, of Markov modeling, when you don't do the model order. Each class is nested model order 1, nested in model order 2, etc. Polynomial fitting. Low degree polynomial, the class of low degree polynomial is nested within a class of higher degree polynomial and so on. That's a typical situation. You have very large class, but you think about it as a union of smaller classes. Remember that each small class, we know what to do. We will get to that. And again, a very celebrated example is the finite state models, was suggested by Ziv. Here, the class depends, the number of parameters in the class is here it is the number of states and the alphabet size. And this is how Ziv declared the individual sequence compressibility. One thing you can notice here is that in order to define it, he first let the data size to go to infinity, and only then he looked at the number of states to go to infinity, which actually tells you that he really didn't found the right solution, because he assumed that you have enough data whenever you try to estimate the parameter of the state. So this is it's scale, right? And nevertheless, it's a great celebrated work, finds that complexity extend the whatever Kolmogorov complexity and so on, attain the entropy of any ergodic sequence. But as I said, there is some problem, and you can notice that problem. Those of you who played with Lamp-Ziv algorithm, it doesn't compress so well. It has great decoding complexity because it keeps growing the dictionary as you have more. It must grow the dictionary as you have more data in order to capture more and more structures of the data. Actually, practical implementation work better than the theoretical one, because intuitively people do not increase the dictionary, but just replace words in the dictionary as you go on. But still, theoretically, Lamp-Ziv algorithm achieve the entropy, sure, but at a very, very slow rate, even for IID processes. So you can now understand the weakness of great results, but the weakness is that you do not try to zoom in into the right complexity of the data. The way you deal with large class model is by just waiting that you have enough data to deal with them. And you sort of first let the data go to infinity, then you are able to increase the complexity. So here we get to the main point of the talk. I have 22 minutes for that.
Don't worry about time. But the thing is, here,
You finish like it.
implicit assumption
Yeah.
is that the data is being generated by some mechanism.
It could be either any source, any ergodic source.
But it doesn't change. In other words, it doesn't flip from one model class to another.
Then it becomes non-ergodic.
Then
Yeah, that's what the assumption of what he proved. He also proved it for individual sequence. For any individual sequence, he achieved the compressibility of that individual sequence. But the way he defined compressibility was not taking into account the right complexity, because he let first the data to go to infinity and then increased the number of states in the finite state machine. Again, great result, but this is the weakness. This is the thing we have to improve. And this is why you cannot apply Lamp-Ziv for explaining what's going on now in modern AI. You need something else.
the context tree weighting algorithm.
I'll get to that. Yeah, I'll get to that. Good question. Context tree weighting is a great example. So here we get to the concept of twice universality, which actually already existed. Yeah, actually it was suggested by Hierarchical back in '85. And essentially what you say, my B class is a union of smaller classes. And I have to estimate not only the model, but also the class. That's why Hierarchical call it twice universality. Actually, he considered a very specific case of Markov modeling. So I have to estimate not only the parameter of the Markov distribution, but also the model order. And as I said, he called it a twice universality. And here it is. Each submodel has its own universal probability, right? QI. So you can say, now we have many subclasses. Each of them is represented by a single probability. Let's take those representative and find representative of the representative, right? So let's find this Q, that min-max. QI are the universal probability of each class, and we look for a single Q that min-max this. Looks like very reasonable, right? What's wrong? The thing that is wrong is sometimes the capacity of that twice universal that I just presented is also large. Because if you have many, many subclasses, you didn't do anything. Before you have a large class, you divide into subclasses, but then now you have many, many subclasses. The number of those, or the richness of those subclasses, the index of those subclasses is also very high. So what do you do? So twice universality is not enough. That's the thing to remember. And okay, so the first thing we tried, we said, oh, what do we want? We want the not knowing the class will lead us into a situation that the extra payment of not knowing the class will be negligible to what we pay so far. So we replace the additive regret by multiplicative regret. Because we said we want the extra payment to be, if we paid much, we are ready to pay some percentage of that. If we pay a little, we want to, again, some percentage of that, not to have additive payment for everything. And so we did min-max of the ratio redundancy, if you want. And you can solve that. It's not so complicated. You can solve that min-max problem too. But that,
the additive penalty has meaning, so you can.
Yeah, I agree. The only thing it means is that when you take Q instead of all those QI, minus log of Q will be some percent as minimal percentage more than each of the QIs, right? We want min max. That's what we wanted. There is no real explanation of code length at this point. That was our first trial. But then we realized that it's, as I said, not elegant. So the better answer is to have, instead of one layer of universality, multiple layers of universality. What was the problem? Remember, we said that we have many subclasses. So let's divide them to classes of subclasses. And maybe you can do it as many times as we want. And the way we define those classes and classes of subclasses and classes, etc., will be determined in a way that we always monitor and make sure that the redundancy, the extra cost is monitored, is not too large. It's only proportional to what we already paid so far by the class complexity.
Many subclasses, they will also grow.
So you divide them again, and you divide them again, and you divide them again. I'll give you an example, but that's the idea. Divide them as much as you want, do it in many, many layers. When you get tired of all those layering, you can just do the multiplicative thing to end up. Now, okay, so you can say, how do I choose those divisions? But the question is, how did you choose the hypothesis class to begin with? Because, I don't know, you just suggested it. And I must confess, I'm actually proud about it. In universal coding, universal prediction, universality at all, there is, if you want, the portion that you can call art and the size, right? That's your, who told you the hypothesis class? That's your language. That's the way you try to describe things. Why did you choose deep neural network? Why did you choose transformers? You call it attention, whatever. That's the sort of the art part. You believe that this is the right language to describe what's going on. But it should be a right language. It should have this hierarchy structure in the right way. That's the art part. And for a given class of models, and I'll show you a nice example, there could be many ways to divide them into layers, depending on your language. I would say this much thing philosophically stronger. There is no best way to divide the big class into subclasses. If there was such a way, you would be able to compute or decide about Kolmogorov complexity, because that's what I'm claiming, right? Something very, very complex. I'm trying to tell you what is the best way to describe it. There is no best way to describe it. It is part of your language. It's part of your assumption in a way. But we extend or relaxed our assumption, not for a given model class, which can be big, but we sometimes there are natural way to do this layering. And I'll give an example. But that's the point. Yeah, sure.
Is there different type algorithms that people are using, like transformers?
People are not using what I'm suggesting. I'll refer to that in a minute. Okay, I'll refer to that in a minute. Okay, but here is an example that I'll do quickly. I think that the canonical example that can explain this multiple universality is an old problem of representing an integer. I have an integer from 1 to infinity. And what is the model class? Model class that, let's say 7, it's the probability 1 that it will be 7 and 0 otherwise. So now I have infinite probabilities in my model class, right? Or the integers. How do I find the universal representative of the integers? There are many intuitive ways to do it. Recently did it, and especially Peter Elias, another exactly the Elias code. And here's the interpretation of Elias code, which actually making it a little bit better, which says the following. Divide the integer into classes. How to divide them? I choose to divide them according to the binary expansion of that integer. So 2 or 3 in one class, 4, 5, 6, 7 in one class, and so on. Now, if somebody told you about the class and you want to find the universal probability for that class, that's easy. They're all deterministic. Then you just give a quarter to each of them. Pay 2 bits. The number of bits that you pay for the universal probability is exactly the binary extension of that integer rounded down. And okay, you can say fine, but now I have also many, many classes. Not just many, many integers, because again, I divided 2 classes so that I have also an infinite number of subclasses. So one way to do it is to stop here and to do the multiplicative thing and to just add a code with 2 log n. And that's the first Elias code, which is very nice. If you didn't know about it, I want to represent, let's say, 7. That's 1, 1, 1. I don't know if it's a 3, 1 or 1, 3 or 7 or whatever, 1, 1, 1. So I cannot just send 1, 1, 1. So what Elias suggests, I need the comma, right? So Elias code, the first code was 1, 0, 1, 0, 1, 1. It's for 7. So you put zeros as long as it continues, and then 1 when it added even points. If you want 3, you would say 3 and 1, you say 1, 0, 1, 1, 1, 1. Okay. And that, of course, you pay 2 log n. That's the optimal multiplicative things that we derived before. But again, we don't like it, so we go to another layer. That's the recursive code of Elias. So what the recursive code is doing, you put the integer according to its binary expansion, and then you add a header, how many bits are in the binary expansion. And then you have another header, how many bits are in the binary expansion, and so on. And then you end up with log n plus log log n plus log 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 n, until you are tired and you say 2 times log 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 n, and you finish. And then you end, right? That's one way, or you continue forever. That canonical example explained to you the concept of multiple universality.
Unique decodability in that. Unique decodability in that.
Yes. But rather, it's not a probability distribution. It's a probability. We look for probability distribution. Decoding intuition just give us a tool to understand what we are doing. But that's nice in information theory. Although we deal with prediction probability assignment, we have decoding intuition. If it's uniquely decodable, it can be translated back to probability and so on. Good. Okay, so that's Elias code, another interpretation with a little improvement.
Coding and decoding complexity.
Hmm?
Like the higher you go.
Yeah, okay. The computational complexity, I didn't care at this point. I'll discuss it toward the end. Okay. A Markov model, I'll skip. That's an old resonance stuff that you actually do MDL for model order and then encode the parameters. And you can see at least the twice universality here, but actually there is 3 layers of universality because you also have to give a code how many, because I mean, if you don't give the third layer, you won't know to deal with possibly infinite memory. So at first I tell you what is the integer, to tell you what is the memory, then I tell the cost of dealing with that memory, and then the entropy. That's reason and MDL with a little bit correction. The log star of k. Probably add it, but didn't represent this way. Okay, so now we get to the context-free weighting, which is an extension of Markov. Now we want to deal with memory, any order, but the memory is not necessarily in a uniform way. That's like in a context tree. And so essentially, what are your model classes? Your model classes are all possible trees of any length. That's a little deviation from the original context-free weighting, where they had to put a bound of the memory, and the extension they did later was not so elegant. So here we have a very intuitive way to extend that. Again, the classes are all possible trees. There is an efficient algorithm, the context-free weighting, which I'll skip, and they prove that this is the redundancy, but they had a finite memory, a limit on the amount of memory. And again, the extension without that limit was somewhat cumbersome. And that's what I'm saying here with the multiple universality. Okay, I look at the data, I fitted some tree model to that data, and now I tell you, that's let's say on the training, and now I tell you the overhead of the training. What do I have to tell you? I have to tell you first how many leaves are in the tree that I found that fits the data. Let's say an integer. If the number of leaves is s, I need log star of s, right? We've seen it. After I told you how many leaves are in the tree, I have to tell you what is the tree. Luckily, the number of, let's say if it's binary tree, the number of binary trees is the Catalan numbers. The number of binary trees with a given number of leaves is the Catalan number, which look like 4 to the s. And you take the log of it to get something that is proportional to s, but not to n. That's the important thing. It's become negligible with respect to n. So now you know the number of leaves, you know the tree. Then I tell you the parameters, and then I encode the data with everything that I just told you. And that explained here we have 3 layers of universality. And it performs somewhat a little bit better than the context-free weighting. But again, the fact it performs better, it's not a big deal because the algorithm, there is no algorithm here. Remember, what the proposed algorithm to suggest is to do a Bayesian mixture of all subclasses, and then another Bayesian mixture, another Bayesian mixture, another Bayesian mixture, and so on. Context-free weighting found a way to do recursively all those Bayesian mixture in an elegant algorithm. That's the thing. And I didn't mention it before. I must confess, at the same time that Willems and the others came up with the context-free weighting, I worked on the same problem with tree modeling with Rissanen and Marcelo Weinberger. And we come up with a great solution. Our solution was not as elegant as that. Our solution was more similar to ERM. But as we looked at the data, we sort of, at each point, we estimated the right tree, and we sort of used it for the next symbol with some variation, and it worked. We got the same redundancy with a less elegant algorithm. I happened to be the editor when I saw William's paper, and I said, wow, such a better paper than ours, and such an elegant solution to the problem we are working on. And indeed, this is really nice thing. And actually, one of the open questions I will throw it here in the air is to find such elegant algorithms for the criterion that I just presented, for this multiple universality criterion. Because if you're going, brute force, you end up with a very complex algorithm. Okay, before we get to neural network, I owe Prakash this example of large alphabet. So large alphabet is really a big class of models. So now you divide it to subclasses. A natural thing to do that is by the alphabet size, right? One class is when I have a single symbol, 2 symbols, 3 symbols, and so on. And then do mixture of each class model, and then do mixture of the integers, and so on. So essentially, what do I have to tell you? I have to tell you what is the integer, k, right? D is the size of the alphabet, which is much larger than your data size. And k is the effective size that you are using, which, when it works, should be smaller than n, because you fit it to the data. But you didn't know in advance what k to choose and which are the symbols that you are choosing. So what do I have to tell you? I have to tell you how many letters are active, what are the letters out of this D, then the parameters, and then, of course, the empirical probability. Luckily, you see, this is negligible with respect to n. This, when k is small compared to d, that behaves like d to the k. The log of it again is k log d, proportional to k. The log d is relatively, even if d is very large, log d is not large, and you end up with good things. After we came up with this and we found some out, it turned out that there was a paper that was sort of forgotten by a guy named Ristad. He suggested from different reasons. He was trying to say that Laplace rule of succession gives too large probability for unknown symbols. I mean, he has like binary, 2 symbols. He says if I see all the time that the sun is rising, probability I give that the sun will not rise is too high. It should be smaller. And he intuitively came up with probability for the unknown symbol that look like n squared instead of 1 over n for the Laplace. And that comes out from this universal probability. However, it is different from good Turing. So what's going on? And that's the point. Nobody said there is a single language to describe complex model. So good Turing, I found a way to describe good Turing. Good Turing also divided the large alphabet into classes. But the way it defined large alphabet into classes is according to the empirical probability that you get. So then I have to tell you, I look at data, then I tell you what was the empirical probability. The empirical probability is nothing but how many ways you partition the integer n into sum of integers and the log of it, right? The way you divide it to some of integer is just empirical probability. So you take the log of this partition. After you know the empirical probability, you have to tell me which symbols have which probability, and then you have the empirical thing. And when you take this probability and make it the predictive part of it, you get something that is close to good Turing, not exactly, but good, the variation of good Turing, one of the variations of good Turing, which you can smooth. And the other thing is that the probability for symbol that you didn't see behave like this. So it goes to 0 like n, but also the size of the alphabet, the big alphabet, D. So it goes to 0 also better than, faster than 1 over n, but in a different way. And empirically, when you compare good Turing to what I showed you before with the classes that of the size of the alphabet, the other model classes, the other art is actually better, give you higher probability for sequences that have higher entropy. So for low entropy sequences, good Turing perform better. For higher entropy sequence, the other modeling will prefer better. So that's, in a way, the way you structure the data. The language that you're using, there are many possibilities and they behave differently, but all of them give you reasonable solution. That's what I'm saying. All of them give you reasonable solution. You do not explode because the model class become too large. In both cases, you can sort of learn the complex model, learn it a little differently because your language was different. And now, of course, we want to go to real thing, like the neural network. So we start with perceptron. Perceptron, one way to look on the model class of perceptron is actually the dimension where the data is. And the reason is, if you have the margin that you have on the empirical data. If you have high margin, you can project the data to lower dimension and work with a lower dimension, fewer number of parameters, smaller class. But that's only one way to do it. There is another more general way. If your model class is sort of generalized linear model class. So the way your model class, the effect between the features and the data, the way it enters also through some linear combination of the features. X is the feature and Y is the data, the label. One example is perceptron. Another example is linear regression, logistic regression, everything. Now, in the over-parameterized case, you pick many, many features. The dimension of theta, and of X for that matter, is much larger than the data. Here again, there is a natural hierarchy. The natural hierarchy is to build subset according to the effective number of coefficients that are non-zero, sparsity. You take this in the linear class and you say all the cases where I have only one theta is effective, 2 thetas are effective, 3 thetas are effective. So you build model classes according to the sparsity, if you want, of the thetas in your vector. And again, the simple calculation tells you that it works because the overhead you pay is again negligible and it compared to the complexity of the true thing that you are using, not to the big thing, not to D, but to K. And here is the problem, and maybe I'll go here. Unfortunately, again, this description also gives you an algorithm, right? We have to do Bayesian mixture over submodels and then another Bayesian mixture. Of course, going over all the subset is exponential in the size of data. You couldn't do it for large D. And there should be an approximate efficient algorithm to do it. But just to show ourselves that it works, we took reasonable D equal 10 in that case. So the number of subsets only 2 to the 10, not so bad. On each of them, we did the Bayesian mixture and the mixture between the mixture and so on. And what we got in the over-parameterized case is actually with small n. N is the data size. D was fixed to be 10. When you have enough n, it's already not over-parameterized, it's under-parameterized. You can fit it, it's nice. I mean, okay, this is the data size, and this is the mean square, the loss. So you see that the blue one, which is it's called here the twice universality PNM, is here. And it's much smaller than, let's say, doing least square estimation, which blow up when you are overestimated or overfitted. But again, and the difference between the dotted and the non-dotted is the variance, the error. Again, we need a computational efficient algorithm for this because it's exploded, become exponential, and we have some ideas. We are playing now with approximate algorithm. Deep neural network, and I'll end with that. Again, there could be many ways to build hierarchy for a deep neural network. You can do it according to the rank of the matrices that exist between the layers. So we chose maybe the simplest way, maybe brute force way, saying we have a big network. It is composed of many subnetworks. Subnetworks are defined by choosing the nodes. Why it should work? Here, the calculation, that simple calculation. What do I have to tell you? I have to tell you in each layer how many nodes I chosen, what are the nodes, and then the parameters, and then the empirical probability each of the small networks. Actually, when it's fully connected network, you don't care so much which you chose in each layer because they're all equivalent. Everything is free. The parameters are free. If you choose 2 here and 4 here, it doesn't matter what are the 2 and the 4 because anyway you train the parameters. So you can skip even the second term. Does it work? It's a complicated algorithm. So I did an experiment. Again, what I'm saying now is a work in progress. The multiple universality can deal with large model classes, for sure. We still lack the algorithm. In order to prove that it works even for neural network, we did the following experiment. We had the large network. Instead of going over all smaller subnetwork, we just randomly picked them. Randomly picked small subnetwork within the big network. How many? Let's say 300. The big network, we picked 300 small subnetworks, but we picked them in a way that have different complexities. So some of the network had, the big network had 1 million parameters, some of the network had 4,000 parameters, and some network had 6,000 parameters. And again, we made sure that the total, so we can compare apple to apples, that the total number of parameters in all the small networks is like the big network. So the total number of parameters in all the 300 networks was the same as the big network, was let's say 1 million. Now, how do we do Bayesian mixture over even a given network? That's also not known. There are heuristics. People do drop-off, and they say it's also to approximate the Bayesian mixture or whatever. Many heuristics, nobody know how to efficiently evaluate a Bayesian mixture over a network. What we know how to do efficiently is stochastic gradient, right? To look for the ERM, but not exactly the ERM, the stochastic gradient. So we said, fine. Remember the stochastic the slide I showed you at the beginning, that picking the maximum likelihood or approximation of the maximum likelihood can be not so bad compared to the Bayesian. If it's sort of pretty good. So we said, okay, we have stochastic gradient, let's pick it. And we did it for those 300 network, not so complicated because each of them had a small number of parameters. And now we do the multiple universality. Now we have to weight them, but the weighting of all those 300 predictors of those 300 networks should be according to 2 things: how well they fit the training data and the a priori weight, which depend on the small network get a higher weight because they belong to a small class of models, which means that you have higher relative probability to each of them. So we take those 2 weights when we weighted the 300 models, and here's what we got. This actually will be my last slide. So what do we see here? The green ones, again, if you're a computer scientist, you may say, I don't interested in log loss, but I said you do interested in log loss. But they sometimes looked at the probability of error, it's written on the side, but then we did everything for log loss, right? So what do we see? The green one is the log loss of the big network. This was a simple data. This was like MNIST, a network of 1 million parameters, 3 layers. And the log loss, you see, it's like 0.24 on the test, of course. the orange and the blue are some mixture of the 300 networks that we randomly picked and use the predictor for each of them by stochastic gradient. The orange, when I talked with some people, said, "Oh, what you are doing is just an ensemble method. You just have an ensemble of models and you weight them." I said, "Right, let's weight them. It's not so bad." The blue one is to weight them according to our theory. That's the result. Initial results which show you that there is some empirical validation to what we are saying. Of course, the theory, the nice thing of what I'm suggesting is that I can explicitly say what will be the overhead, how far I will be from somebody that knew the truth. Which, if you agree to my way of language or my way of putting this hierarchy of models. And this is asset crude, which also works for probability of error. Yeah. So we went from, let's say, 19, it was MNIST, so we started with, I don't know, it's not written. So we improved also with the probability of error. But there is not much to prove there because MNIST is an easy problem. Okay, I said elephant in the room, what is the right hierarchy? How we choose that? I claim there is no solution because it might be undecidable, but again, it's nice that we, as I said, we still have a part of his art, philosophy to play with and think about it. Thank you very much.
Thank you very much.
And last question in the middle, of course.
No, thank you for the questions. Chanik, you had a question.
Answered in the middle. Okay. Go ahead, yeah.
You had the general classes that you described, and actually you were dealing with probability measures. So
Yeah.
they were there. And when you come to the neural network, somehow you're using the weights to form probability distributions. How do you form the classes?
Oh, that's easy.
Ah.
That's easy. Each network,
Yeah.
the way designed, doing at the end the softmax, what's called so a network. As I said, now everybody's agreed to have a probability and log loss. So each neural network that people use doesn't give you a deterministic fit, it gives you a probabilistic fit.
Oh,
So, so the way,
by definition.
exactly by definition, at this at least we won. We convinced the world that you should not come with a deterministic prediction, you should come with a probabilistic prediction and use log loss. And indeed, neural networks that are used in practice have this softmax at the end, which give you a probability distribution according to essentially the fit, which you also train depending on the parameters.
Thank you.
Oh, yeah.
Yeah, here.
Here?
No, so when you say approximate the universal predictor,
Yeah.
you need to understand what exactly is going on.
Okay. Okay, so that answer maybe a little bit for what Prakash said. What we had to do, given a subnetwork, theoretically, we have to find out a prior over the parameters, do a Bayesian mixtures. I mean, each choice of parameter give us a probability by this softmax. Now take all these parameters, take the prior, average according to the prior, and get the universal probability for that small network. Do a Bayesian prediction and not just ERM prediction, just fit parameters to the data. I don't know how to do it efficiently. So in the literature, people thought about Bayesian modeling, but the only solution that I know of are heuristic, even stronger than this heuristic. They say, oh, if you just drop off some edges and do this and do that, it sort of should approximate the Bayesian. Why? I don't know. But they have some intuitive explanation, let's call this. But forget those explanations. Let's take the stochastic gradient. Anyway, we are talking about small networks, so it's not so bad in a way. You don't, the drop-off sort of seems to take out, make large networks, small networks or something. So I said, okay, for each subnetworks, the stochastic gradient behave like the predictor. And then I have to weight it. If you remember the slide that I gave early on, or much earlier, I go to an explanation of what is the base thing. That's, I think it's a nice intuitive slide. Yeah, here it is. What does this slide tell you? That the ERM, the stochastic gradient, in a way approximate the ERM, which means we try to achieve the maximal, the theta that maximizes this term. Okay? In a way. So according to this Bayesian mixture, I'm not thinking on the maximum, I'm sort of weighting all the thetas. However, if for some reason there is a strong estimate, then weighting, well, the weight mostly depends on how it fit the training. And if that SGD fit the training well, choosing only that one, or doing Bayesian mixture of all of them is almost the same. So I assume that for the small network, I have that situation. And actually, this was the only, the easy algorithmic way we can do with my student, right? It took some Python code and ran it, and we got the SGD.
So the training is directly on these W theta weights.
Yeah, all the weights of the network, exactly, all the parameters of the network. Yeah, I choose the small network, and I went over all its parameters, definitely, by doing this SGD. That is the algorithm. Exactly. So the SGD replaces the Bayesian within the network. And between the network, how did I do the hierarchy? I did the hierarchy in the sense that for each, depending on the number of parameters, if you want, how that define the class. So each class has, in a way, a weight that, you remember another slide that I saw, that approximately the capacity is proportional to K log n. So you can take that into account in weighting the probabilities, and you also have to weight how it feeds the data. So that's how I weighted all those 300 models.
Maybe one more question.
But again, there is a lot of work to do here, and it's far from, I mean, I still feel that it's still crude. We have to really get an efficient recursive maybe algorithm to solve that problem. Yes. Sorry.
So like you have this large net, you select these small.
Yeah, randomly, yeah.
So your training is basically kind of a two-stage training.
Yeah.
In which you.
Yeah, I train in parallel. I take all those three networks, train in parallel. Then I weight them, and then I get the performance that are given in the blue.
So once you are training both the parameters of the small networks and the weights that are associated with them.
Yes. And then
what happens if you like fix the inner network, like
the what?
So
I just pick what? It's only one small subnetwork?
no, I mean as like you freeze the small subnetwork
Yeah.
and only optimize over the weights of
The weights of what?
the theta weights that you have.
But no, this is known in advance. By the way, that's easy. The weight for the class are given by by how I achieve the capacity, right? That the extra code length should be K over 2 log n. And okay, so the fix for each class, I know that. What I don't know is the parameters, and I train them, and how they fit the training data. Okay, this is used out.
Hello, can you hear me? Can you hear me? My name is Tomashko. I am joined this nice talk. Thank you very much. Can I have a question?
Definitely.
Okay, so I am curious about the connection of other machine learning techniques. So for example, for linear predictors, we can apply penalized regression, lasso, for example. Or my other thing in my mind is the boosting algorithm that basically combine small estimators into a strong estimator. So how the relation, what are the performance, comparability? This is what I would like to ask.
Okay, I don't do a comparison to boosting, but what you are saying is may indicate a similar intuition that you want to weight more smaller models. In boosting, the Bryman paper has a different way to do the weighting or whatever. But in a way, I mean, many of the ideas I'm now presenting, I mean, in one end they are new because they're posed in the context of universal prediction and so on. But it point out to existing ideas, existing solutions. One thing I didn't mention, one way that is very close to what I'm saying is what's called recursive or layered empirical base, which also do something similar, with again, with a different kind of intuition, a different kind of motivation, but we end up in a similar way. You can say that instead of choosing the model classes the way I chosen, you say that the only thing I did is just choosing a different prior that for some reason prefers smaller things over higher things. So in a way, if I build it as a prior, not an hierarchy, then I'm getting similar results. And I agree. The difference is that is where you start from. In the way I present things, the prior is an outcome, is a result. What you start with, the art part that you start with is the language, is the way you describe the tools that you are using to explain the data. So there are similarities of the proposed algorithm to other methods. I mentioned ensemble method, boosting, and others. I'm sure I cannot tell you now the exact relations, but I'm sure there are some relations, which is good because those methods were suggested and work. So it's good that we now sort of have them in the right framework of a universal information theory.
And in some sense, so I guess that I am not, so I am also mathematician, so not, I don't work in machine learning. Just I know that there are benchmark models or data. And maybe it would, so then you can try to compare the performance.
You're right. You're right. We should compare them.
And then the performance will say
that we have to do, and it's a work in progress. You are completely right. And the thing that will make me happiest is indeed to show how many or maybe all of those statistical techniques that have been suggested for different reasons, some of them are heuristics, fall into this kind of theory.
Oh, I see. So what you say is that the other prior, choosing the model classes, would be conditionally uniform over each class, but the conditioning probability.
Yeah, you can think about that, but with small refinement, that because you want to have the capacity at each layer, with a small refinement. But you are right. That's why intuitively it works. So again, when I tell it to some of my colleagues, people say, "Oh, okay, you deal with large model, and I'm saying it explicitly. You gave up this uniform convergence. Sure, why do I have to have uniform convergence? And the convergence is depending on the data. Great, definitely. If the data fits complex model, you need it converges slower. If the data is explained by simple model, it converges faster. So all the things are, and again, there is all this phenomena that people observed in machine learning, like flat minimum. What is flat minimum? Flat, I mean, they say you train your neural network, and if you end up with choice of parameter that essentially lie in a flat minima, which means that you can change the parameter value and nothing changes, then you can trust it. I'm saying, great, that actually says that you end up in a subnetwork because many of the parameters are irrelevant. You don't care about them. That's actually indeed saying empirically what I like to say. There is also another, when I gave the talk to computer scientists, oh, we have this, if you heard that, they're great in inventing names, attention, etc. So they have this name, lottery ticket assumption. I don't know if you are aware of this paper. So they're saying that indeed, in the way you are training, you are trying different things. It's like you are playing the lottery until you end up with a simple model. Good, fine, that's what I agree. So, and then there are some papers on that, and it's a nice observation. Again, it fits, I think, the theory I'm just presenting. I'm trying to get a unified information theory of the learnable. We want, I mean, information theory and learning must be strongly connected. That's what is information theory. It's extracting information from data, transferring information. Everything is information. So, sorry for a long answer to a specific question, but it's okay.
Thank you for a very thought-provoking talk.
Thank you again. See you around.
Thank you.